Okay, hello everyone. So welcome you guys to the Smart Math academic seminar. And today is our great honor to have Professor Dickey from North Carolina State to give a talk. So Professor Dickey received his bachelor degree in chemical engineering from Georgia Institute of Technology in 1999. And then a following PhD degree from the University of Texas at Austin in 2006 under guidance of Professor Grant Wilson. From 2006 to 2008, he was a postdoc fellow in the lab of Professor George Westside at Harvard. And he's currently a Camille and Henry Dreyfus Professor in the Department of Chemical and Biomolecular Engineering at North Carolina State. And he is a winner of the ASEE Southeastern New Faculty Research Award and the University Faculty Scholar, and also the prestigious National Science Foundation Career Award. So Michael's research interest includes soft matters and for soft and stretchable devices. And today he will give us a talk entitled Liquid Metal Beyond the Terminator. So I think Michael, with further ado, I think all floor is yours.
Thank you so much. I think you have to stop sharing maybe first. Oh, there we go.
Yeah.
Okay. Can you see my PowerPoint?
Yeah, perfect. Yeah.
All right, great. Thank you so much for the introduction, and thank you all for being here. I know that this past year has been difficult and people are tired of doing things online, but I'll do my best to keep this entertaining. I'd like to give you a sort of a high-level overview of some of our work on liquid metals that we've done here at NC State. And this is the first time I've given a talk in Beijing, I guess if you can call this virtual talk in Beijing. So I thought it was appropriate to start with kind of this most important slide. This is a photo montage of many of my friends, former students, and visitors that have come from China. So we've had a lot of really great students and people that have come to our lab at NC State. And these are just a small sampling of some of these people. So I welcome all of you to come visit us and come to beautiful Raleigh, North Carolina. So speaking of which, this is where I live. This is Raleigh, which is the capital of North Carolina. So this is the Atlantic Ocean. So up here would be New York. Down here would be Florida. So we're kind of in the middle of the East Coast. And believe it or not, Raleigh is ranked as one of the best places to live in the entire United States. It says top 10 best places to live. So it's a really nice city. It's the biggest university in the state of North Carolina. It's North Carolina State University. This is our building. This is our library. It's a very nice place, and I hope that you'll come visit it. So in our group, we work on a number of different things that are united by the importance of these words: interfaces, patterning, and soft matter. So I'm just going to show you a couple videos just to give you a high-level overview. So one of the things we work on is actuating polymers. And so in this example, there's a piece of plastic, and we shine light on it, and we can get it to fold. I'm not going to talk about this. I've given some examples of some of these publications if you're interested. What I'm going to focus on today is our work on liquid metals, as shown in this picture. So the motivation for this work is captured by this really beautiful image that I found from the internet. And the idea here is on the right is the human body, which is mostly made of soft materials. And on the left is a robot that is made out of rigid materials. And so most of our devices, like our computers or even robots, tend to be made out of rigid materials, but yet our bodies tend to be made out of soft materials. So we're working on ways to sort of bridge this gap to make devices that are truly soft, that could be wearable or worn comfortably on the body. So to do this, we're using liquid metal. And liquid metal is interesting because it's highly conductive and also highly stretchable. So this is a plot of the conductivity of different materials. and as a function of strain, how far you can stretch it. So one way to make a stretchable conductor is to take a rubber material and to add fillers that make it conductive. And when you do that, you can take something that's very stretchable but not very conductive, and you can make it more conductive, but typically at the expense of making it less stretchable. With liquid metals, we can get the best of both worlds. We can get something that's high strain and very high conductivity. So this is a video, and I'll let you hear it. Okay, so in this video, there's a rubber tube basically that's filled with liquid metal, and when we stretch it, there's no degradation in sound quality. It's basically got the conductivity of the metal, but it can be stretched to very large strains because of the rubber material. So let me tell you a little bit more about this. What is this liquid metal that I mentioned? So most people, when they think of liquid metals, they think of mercury, which unfortunately is toxic, so we don't want to use that. There's also these elements that are over here on the left side of the periodic table, but these are very dangerous. They tend to be explosive or radioactive. So that really leaves gallium as the only material that's really, really practical as a liquid metal. So gallium technically melts at 30 degrees Celsius. So that's a little bit above room temperature. This is a picture of a crystal of gallium. And if you add in other metals like indium, for example, you can depress the melting point to below room temperature. So when you mix these two things together, you get a liquid. And the composition we use is called the eutectic gallium indium. And eutectic just means the composition with the lowest melting point. That's about 75% gallium. So this material has a bunch of interesting properties, and I'm going to tell you about it. I'm biased, but I think it's one of the most interesting materials on the periodic table. So first of all, its viscosity is like water. It's literally twice that of water. The conductivity, both the thermal and the electrical conductivity, is metallic. The surface forms a native oxide. I'm going to be talking a lot about that today, so make sure you pay attention to this. I'll mention in just a second. The surface tension is the largest of any liquid at room temperature. It's about 7 times that of water, or maybe even 8 times. It's huge. The vapor pressure is about 0, so that means you don't have to worry about breathing it. So let me show you this video. This is a little bit of the liquid metal being squirted out from a syringe, and you can see that it flows very easily because of the low viscosity. If you swirl around the container, you can see the liquid flows, but it holds this kind of weird shape, and that's due to this oxide layer. Now, if you dissolve away the oxide layer, the metal will simply bead up due to surface tension. So we do that using sodium hydroxide, which is a base. So this is kind of a really key idea, is that this metal reacts with air and forms a very thin oxide on its surface. Now, the last point I want to make is, a lot of times people ask about, well, toxicity, is it toxic? And actually, there's been several studies. One was by my friend Zhen Gu, who showed that you could actually use liquid metals for medicine. And also, one of my former students and her husband have characterized the toxicity of gallium and shown it's actually quite low. So the good news is it seems to have low toxicity. Now, let me tell you a little bit more about this oxide layer. Pretty much all metals other than, say, gold and platinum will react with air and form what's called a passivating oxide, which just means it forms an oxide and it stops. And so this is a picture of aluminum foil, and it reacts with air and forms an oxide. In the case of the liquid metal, it also forms an oxide layer, and that oxide layer is about 3 nanometers thick. It's very, very thin, but it has a profound effect on the way this stuff behaves. So to drive home this point, this is a video of the ability to 3D print liquid metal. And if you take the metal and you suck it back into the syringe, you can see the oxide sort of wrinkle. And this oxide layer forms so fast and is so strong that you can actually 3D print this material at room temperature. So for the first time, you can truly print metals at room temperature. And so this, again, is liquid the whole time, and it's held together entirely by this very thin oxide layer that forms spontaneously. It forms very, very quickly. Now, in addition to stacking droplets, you can also do a burst of pressure, and it will shoot out the metal and form a solid skin in midair. The structure is like a garden hose. You can drag it around and form electrical connections. And then this is a dead bug. So these are the eyes of the bug, and you can see that this printing is very, very gentle and truly, room temperature. So that's one way you can pattern the metal, but there's other ways, including injecting it. So these are very unique things. Usually you cannot do this with metals. So in this video, there's some microfluidic channels, which you can sort of see here. And there's a droplet of liquid metal placed over the inlet. It's a little hole. And the student, you can see the student's reflection here. And the student has put it inside of a vacuum chamber, which has pulled all of the air out. Now, if you watch, you'll see the student is going to come and turn the valve, which will let air back into this chamber, and it will push the metal into the microfluidic channel. So it's a very simple, hands-free method of patterning the metal in a very simple way. So we've used this to inject liquid metal to make things like antennas and electrical circuits. This is a coil for wireless power transfer, and they take on the mechanical properties of the polymer. So if you inject it into silicone, it's like a silicone rubber. It's very easy to stretch. Now, there's some other interesting things you can do. For example, you can put the liquid metal, as shown here, in a special polymer. This is a self-healing polymer, and there's electricity going through this polymer that's lighting up this LED. Now, you can cut this with a pair of scissors, and it will break the circuit, and you can see that the light turns off. And the key thing is that the liquid does not leak, does not come out. In fact, it oxidizes so fast that it stays flush with that interface. So when you bring it back together, the circuit will heal electrically, and the polymer will also go back together because the polymer is held together by hydrogen bonding. And so if you wait about 10 minutes, the polymer will go back together and it will heal electrically. You don't have to do anything, you just wait, and the polymer will completely self-heal. And so it's regained its original mechanical properties. Now, one of the interesting things about liquid metal is that you could potentially make circuits that change their shape. And so, as you know, it's very easy to inject liquid metal into these microfluidic channels, but it's not easy to pull it out. So if you try to suck the liquid metal out of one of these channels, you'll see that there's liquid metal residue. It sticks to the walls of these channels. In fact, liquid metal sticks to almost everything, which is very surprising because these liquids have very high surface tension. They should not stick to things, and it's only because of this oxide layer that they do. So to illustrate this, this is a droplet of the liquid metal, and if you inflate the droplet, it's called advancing, you basically make the droplet bigger, and then you suck the liquid back into the syringe, you'll see that the droplet gets stuck. It stays stuck to the surface. So you see it's pinned here on the edges. Now, if you put the metal on a rough surface, you can spread it out and then pull the metal back into the syringe, and it doesn't stick. So this key idea is that rough surfaces prevent adhesion. So now the challenge is, if that's the case, how do you make the inside of a channel rough? So here's a piece of plastic that's been printed, and we want to make the inside of this channel rough. So the way that we did this was by injecting some silica particles, these little grain particles, along with a little bit of solvent, and it makes the walls of this sticky. The particles stick to the wall, and we then rinse these channels out, and you're left with this rough surface. The nice thing about this coating, which is it's really nice, is that when you do this coating, so this is a piece of plastic that's been 3D printed, and on this side there's no coating, and on this side it's coated. You can't tell any difference. In fact, this coating is transparent because it's so thin. If you put liquid metal on both sides, you'll see that on the uncoated side, the metal sticks, but on the uncoated side, you can pull it right off. And if you look at this coating, you can see it's got these silica particles, and it makes this rough surface, which you can see are, a few nanometers in size. So we did this on a 3D printed plastic, and we injected the liquid metal. So here's the liquid metal inside of this 3D printed part, and then we pull it back out, and you can see that if we don't coat the channel, it sticks. It's really difficult to remove it, at least remove all of it. But if we coat the channel, so this is silica coated, you can see we inject the liquid metal, and then we empty it, and no problem. So then we did another experiment where we dropped liquid metal droplets and we used a high-speed camera. And on the left, you can see on these rough surfaces, the droplet will actually bounce. On the right-hand side, when it's on a smooth surface, the droplet will come down and it will stick because of the oxide layer. In fact, you can see that it stays flattened. So kind of the key idea here is that these rough surfaces will prevent, I'm going to play this one more time. These rough surfaces will prevent adhesion. Okay, I'm going to switch topics for just for a few minutes here and talk a little bit about color. So this is some work I'm really excited about. The motivation for this work was the idea that in nature, organisms use color change for survival, for mating, for camouflage. And actually right now, hopefully you're listening to my talk and you're watching a computer screen, so human-machine interface, that's using color change for communicating information. So we decided to try to do this in a soft device. And I had a really good Chinese student named Yang who visited us for about a year. And he injected these liquid metal into the silicones that had this blue pigment. Now this pigment, if you warm it up, it will turn white. It actually changes color. And the way that we do this is just by simply running electricity through this polymer. So in this example, we patterned the liquid metal like our NC State logo. You can see the color change of the logo in terms of the thermal imaging, but also in terms of the polymer. And the red and the blue pigment actually change at different temperatures. So if you mix the red and the blue, you get purple. If you run a little bit of electricity, the red disappears and you get blue. If you run more electricity through this device, the blue disappears and you get white. And so then if you let it cool back down, the pigments go back to the original color. So they'll go back first blue, and then the red comes back and it appears purple. So this is really, looks very nice, but I would say sort of obvious. Where this gets interesting from a scientific standpoint is because we're using liquid metal, we can actually deform the circuit. So if you take basically this piece of plastic and you push down on this circuit, you change the dimensions and you change the joule heating. So when you deform the circuit, you make the local resistance higher and you cause it to change color. So an illustration of this concept is here. This is a piece of silicone that has a liquid metal wire in it. And we're running electricity through here. So there's electricity, but there's no color change because the resistance is not high enough. But when you start stretching this wire, you make it longer and you make it narrower. And that changes the resistance. So then you start to see a color change due to joule heating. So this is interesting because you have a responsive material that couples mechanical properties, so stretching, electrical properties, which is resistance, and optical response, which is color. So this gets even more interesting. And to motivate, where this is going, if you think about trying to pick up an object like an apple, the first thing you do is you sense it, usually with your eyes or your hand. And then your brain does some computation and your muscles contract to pick up the object. So if you were trying to mimic this in a synthetic system, you would maybe make a sensor, have a computer chip, and then have a motor. And the problem is if you try to do this on a robot, it can become very complicated. So if you think about one of my favorite robots, C-3PO, you might remember in the movie Star Wars, it's when he got his arm ripped off, you could see all these wires. And in the human arm, there's about 1 million different nerves. So imagine trying to make that many wires to connect up that many sensors into a real robot. So there's this interest in, maybe we could just get rid of the computer. What if we could just get rid of the computer chip and actually have the sensor and the motor work together? And this sounds like a really great idea. And in fact, Mother Nature already does this. So this is an octopus, of course, and the octopus has about 2/3 of its neurons in its arms, which is really remarkable because in vertebrates like humans, of course, our brains are centrally located in our skull. So this raises lots of questions, and this is, people call this distributed logic, where you put your logic elements actually in your material. Now, we're a long way from being able to do this in a convincing way, but we've taken a small step. And what we did is we created a circuit composed of three parts, A, B, and C. And we turn it over, so this is region C, and we run current, and the current goes through A, B, and C. And so in region C, there's not enough current to cause a color change. But if you push in region A, that redirects the current here, and you get enough current to cause a color change. If you push A and B, you get a different state. So again, there's no transistors here. This is just silicone and liquid metal. And all we're doing is, based on how we make the circuit, we can do very, very simple logic. You can think about it as like a 0, 0, 0, 1, 0, 1, 1, 1, 1, or something like that. So speaking of touch sensing, we've also done some work with another really wonderful student from China, Jia, who was just here about a year ago. And he did work on using capacitive tactile sensing. So the idea here is that if you touch a material, you can detect the touch by detecting changes in capacitance. So here you have a dielectric material with two electrodes, one on this side and one on this side. And this is just, a very basic equation. The change in capacitance that results from touching is due to the change in this height, delta D. So if you want to make your sensor very sensitive, there's a few ways to do it. One is to decrease the modulus, to make it very soft. Another is to increase the dielectric constant, or make the dielectric constant change as you press the material. So there's been some really great work in the literature, I call them tricks, with silicone. The first is to soften the silicone using microstructures. So instead of using a capacitor made of a slab of silicone, you actually use pyramids of silicone, and this is from the Bow group at Stanford. And so this results in greater sensitivity. Another really nice work is from Mike Bartlett and Carmel Majidi, where they mixed liquid metals in with elastomer, and that increases the dielectric constant, but it doesn't make the material stiff, so it keeps it very, very soft. So inspired by this, we set out to make some particles, and this is actually very easy. You can just take liquid metal and essentially stir it or sonicate it, and it will break up into little droplets. And we have a review on this, on these techniques. And so Jia, the student that I mentioned, this was another review from a really great Chinese student, Yiliang. And so anyway, we did this, and we mix liquid metal. So here's the liquid metal with some sugar and some silicone called EcoFlex. And we mix them together, and then we dissolve the sugar, and that leaves behind a foam. So you can see this is what the foam looks like. The foam consists of the liquid metal mixed with the silicone. And so as a result, it's very, very soft. And so the beautiful thing here is if you take this foam and push on it, you effectively increase the dielectric constant. And so this is very, very soft, and you have a high dielectric constant. And so we can measure this change in capacitance as a function of stress, basically, as we push on this material. And there's several sets of data here from, this is 0% liquid metal all the way up to 40%. And as you can see, this is 0% liquid metal. This is just silicone foam. And if you add more liquid metal, you can actually greatly increase the capacitance. So this makes your device more sensitive. And so there's a measure of sensitivity, which is change in capacitance divided by initial capacitance. And I actually personally don't think this is a very good metric, because if you look at this equation, if you want to make a really good sensor, according to this metric, you would just make C0 basically 0. But nobody wants a sensor that has that can't measure the initial capacitance. That doesn't make any sense. So what we got here is an initial capacitance that's larger by adding the liquid metal, and also more sensitive. So this is really nice. Now, one of the interesting things that came out of this is what we call piezo permittivity. Piezo means touch, just touching something, and permittivity refers to the dielectric constant. So this is a plot of the dielectric constant of this foam material as a function of compressive strain. And again, you can see down here, if the silicone doesn't have any liquid metal, it's a very low dielectric constant. It's very low, like almost like air. But if you add liquid metal, you can make it larger. Now you'll notice something very interesting. First of all, the dielectric constant goes up, and then very strangely, it goes down. So let me talk about this. So here's a line that divides the part that goes up and the part that goes down. And the part that goes up, this is easy to understand because remember, we have a foam, and when we push the foam, we're just pushing the air out. And so we're taking something that has here a lot of air, and here it has less air. Now, once all that air is pushed out, we get actually a decrease in dielectric constant. So we call this a negative piezo permittivity. And the reason that we think that it's going down is because the liquid metal fillers are actually changing shape. And that change in shape actually changes the dielectric constant, which is really fascinating. As far as I know, this is the only example of a material that does this that's reported. That is liquid metal fillers. So the exciting thing from this work is that if you take all the commercial elastomers and you plot it versus the modulus and the permittivity, you can see that most commercial elastomers fall over here, which means they have a relatively high modulus for silicones, and the permittivity kind of spans these values. In our case, we can make a silicone foam, but unlike just regular silicone foams, we can make it much higher dielectric constant by adding the liquid metal. Now, speaking of this piezo effect, there's some really nice work from my colleagues who I've mentioned here, Xiang, who is one of the leaders on this, as well as Professor Li, where, again, piezo, remember, it means touch, and conductivity refers to electrical conductivity or thermal conductivity. So here we take, again, silicone, we mix it with some iron powder and liquid metal. And it doesn't have to be iron. There's other metals that would work. And you mix them together. This is what it looks like. You get this composite material. Now, why is this interesting? Let me tell you what typically happens in composite materials. So this is some really nice work from the Samaya group in Japan, where they mixed silver flakes with rubber. And they were able to make a stretchable conductor that worked really well. But as you might guess, if you start stretching these composite materials, the conductivity eventually goes down and then eventually fails. So typically when you stretch a composite, the resistance will increase or the conductivity will decrease. So why is that? Well, if you have a composite and you have particles and you stretch them, you typically pull them further apart, which means they're going to be more resistive. And in our case, we have liquid metal along with these solid fillers. And when you stretch it, you actually decrease this gap between the fillers and it becomes more conductive. Not only does it become more conductive, but it becomes much more conductive. So this is the resistivity plotted as a function of tensile strain. And you see this is quite a small strain. And the resistivity drops by 3 orders of magnitude. So this is really great for sensing. In fact, if you put this material on a finger and you measure the change in resistance, you can see that when you bend the finger, the resistance goes up and then you let it go. And so what's remarkable about this is that this is on a log scale. So this goes up by 2 orders of magnitude or 3 orders of magnitude due to this liquid metal structure. Now, these composites that I showed you, typically if you want to make them electrically conductive, you have to put a lot of liquid metal into the composite. So this is the silicone mixed with the liquid metal. And as you can see here, you have to put high loading, a lot, like 80, 90% to really get all those liquid metals to become conductive. So we have this collaboration that shows that you can actually get around this and achieve conductivity at low loading. And the way that we do it is by using what's called dielectrophoresis. We basically take electrodes and apply a voltage, which creates electric fields, which causes these particles to line up together and combine. So this is a picture of these liquid metal particles in silicone, liquid silicone, and we apply the voltage and you can see that they're lining up. So let me show you a video of this. Again, these are gold electrodes. The clear stuff here is silicone, and then these black things are the liquid metal particles. When we apply a voltage between here and here, you can see that the particles start moving and they actually line up and they connect because they're liquid. They're easy to connect together. So the beautiful thing about this is we can get conductivity at 5 or 10% loading, whereas typically with composites, you need like 80, 90%, something like that. The other interesting thing is you can make a self-healing ink. So this is a very simple circuit. We literally cut it so that it's not conductive anymore. So we cut the silicone out, pull it out, and then we backfill it with this ink, which is just liquid metal in silicone. And you can see it goes in there. It's not conductive. Remember, it's at low loading, but if you apply the voltage, you can get the particles to line up. The circuit becomes conductive, and then you can cure the silicone, which will cause it to heal. So this was done with Professor Matthews and some really wonderful students from Singapore that came and visited my lab. One of the other cool things about these particles is that if you measure the resistance between these two copper electrodes and you start stretching it, remember, normally the resistance should go up, but here the resistance stays very constant. And we think that this is due to the sort of the serpentine shape that these liquid metal structures form. Okay, I have one last thing I want to talk to you about, and it's going to be a little bit of a transition, but I'm still talking about liquid metal. And that is that, you know, liquid metals, if you remove the oxide layer, they actually have enormous surface tension. So this is the liquid metal inside of a vial of sodium hydroxide. So the sodium hydroxide has a very high pH, and it will remove the oxide layer. So when you shake this thing, it will break into droplets, but it'll very quickly go back into one droplet because it's trying to minimize its surface energy. So with the oxide, if we do have the oxide, so this is the liquid metal sitting in some salt water, it will hold its shape until you remove it. And we can remove it using electrochemistry. So here we take 2 electrodes and we apply a voltage. So I'm going to play this one more time. This is the liquid metal. This is salt water. And we just take 2 electrodes and we apply a reductive potential. Now that reductive potential removes the oxide layer and causes the metal to beat up, and you'll see bubbles form. Those bubbles are hydrogen bubbles. So this is the very oversimplified reaction, but basically oxidized gallium, which is on the surface, you can reduce it and it forms liquid. So what's interesting is you see here, it beads up, it tries to minimize its area. So we showed that you can actually do this in a microchannel. So let me pause this for 1 second and explain what you're looking at. These dark lines are the liquid metal. And there's over here, there's a reservoir of liquid metal, and there's an electrode that we connect to it. Over here is a reservoir of water, and we connect an electrode to it, and we apply a voltage. When we apply the voltage, you'll see that it removes the oxide layer, and it causes the metal to withdraw from the microchannel. So this allows us to selectively remove the liquid metal from these microchannels because, again, we are simply removing the oxide layer from this leading edge, and the metal is trying to beat up here to minimize its energy. So this is really cool because you can actually solve a maze using liquid metal. But the real challenge from a physics standpoint is how do you get the metal to go back inside the channel? Now, if you just simply took the 2 electrodes and you switched them, that might be, you know, kind of an intuitive approach. But the problem is, instead of reducing the oxide, you would actually deposit the oxide. You would oxidize the surface. And so nothing should happen. And so we did this experiment. So this is a droplet of this liquid metal, eutectic gallium and indium, and it's sitting in sodium hydroxide. Remember that what I showed you where it beads up? And you can see that the metal here has very high surface tension. In fact, it's almost a perfect sphere. So we're going to apply a positive voltage. And remember, what you would expect is that the surface should form an oxide and nothing interesting should happen. But when we do this, we found something very remarkable. And that is that the metal spreads like crazy. It actually flattens like a pancake. And if you look carefully at this leading edge, let me back up a little bit, you can see that it's actually not really wetting. It doesn't have a wetting contact angle. And this forms this weird bridge with this needle, and there's stuff on the surface. There's so many weird things here. But the weirdest part about it is that the fact it's flat, because the liquid metals have enormous surface tension. So let me show you another fun video. This is looking top down. So let me describe this. So this is looking top down. We're applying a voltage from electrodes underneath these liquid metal droplets. And when we apply the voltage, you can see that the metal will spread due to gravity. Gravity pushes it into this mold, and it forms these cool shapes, star, triangle. But then when we turn the voltage off, the oxide dissolves and it goes back into a sphere. And so this is kind of a long story, and I don't have enough time to tell everything, but I want to just tell you the main points. The main point is that this oxidation really lowers the surface tension. So if you wanted to lower the surface tension between, let's say, water and oil, you would do it by adding soap. We call this a surfactant. The soap goes to the interface between the oil and the water, and it can form something that looks like milk. Now, in our case, well, in the case of soap, it's very easy to add the soap, but very difficult to remove it. In our case, we apply 1 volt and we deposit the oxide and it flattens because it's got a low surface tension. Basically, gravity squishes it down. But then we can completely remove it using -1 volt and it goes away. So it's completely reversible. And it's a huge, huge change in tension. It's really hard to appreciate, but this is like a record setting. Nobody's ever achieved such a large change in tension using like soap, for example. So we did some experiments, and the experiment again consists of a little wire connected to the droplets, and we apply a voltage. And when you apply the voltage, the surface tension gets lower and gravity causes the metal to squish down. We use this to characterize the surface tension, and actually we found at just the right conditions, it looks like the surface tension is 0. Now, if a surface tension is 0, there should be no penalty for it to form additional surface area. So we did this experiment with Karen Daniels, and the experiment again consists of a droplet in a little dish with sodium hydroxide. So that's basically dissolves off the oxide, which is important because it allows the metal to flow as we apply this oxidizing potential. And we have a counter electrode that goes around the outside. So at just the right conditions, this is what we see. So here's the droplet of liquid metal. Again, you're looking top down. We apply the voltage. It starts to spread like a pancake. And not only does it spread, it starts to form fractals. So remember, the electrode is here. Sometimes these fractals will break. And when they break, the oxide will dissolve. And you can see that it typically will beat up, because if it's not connected to the electrode, it's not getting the electrochemical reactions that drive this process. So again, I'm sorry I don't have time to tell you all the details. I hope this just gets you interested to learn more. But basically what we think is that the surface oxidation, electrochemical oxidation, deposits species on the surface that help lower the surface tension. So more recently, we use this to deal with what's called Rayleigh instabilities. So if you turn on your faucet and you'll see water dripping out, you'll see that it forms droplets. And this has been known since the late 1800s. It's very well known, and it's called the Rayleigh instability, named after Lord Rayleigh. It's driven by surface tension. Basically, the liquid wants to form droplets. So here is water, and of course, if you increase the velocity, you can create a cylinder of water, but it will still break up into droplets. The time required for this to happen, this tau term, is scales with the diameter of this cylinder to the cubic power. So what that means is if something's really small, like a small stream, it should break up really fast because it should take very little time. And also, if something has a very large surface tension, it should also happen very fast. So we took liquid metal, which remember has the largest surface tension of any liquid, and we pumped it from a 100 micron diameter. So that's a very small D. And we start pumping it, and you'll see it forms droplets. But as we start increasing the voltage, the tension gets lower, and which means the droplets get smaller and smaller and smaller until eventually it comes out as a wire, which is crazy. And if you apply a big enough potential, like 1 volt, it actually the oxide gets too thick and it starts looking kind of like candle wax. It's beautiful, but it doesn't flow very smoothly. So we found, let me pause this video. We found the tallest container that we could find in our lab, and you might be able to see this very thin line. This is the liquid metal wire. This is like the size of a human hair. So if I pull out my hair, it's made out of liquid metal. So it's 100 micron diameter, and it's about not quite a meter, maybe half a meter in length. So as you'll see in this video, here's the nozzle, and let's see if this will work. So I'm pointing to the wire. You can see it's very, very long, and it's flowing at a very slow velocity, and it flows all the way down to the bottom of this tank. So this is pretty interesting. Okay, I wanted to leave a minute or two at the end of my talk to talk about some exciting future opportunities that I think are worth checking out. So there are a number of groups in the world that are working on liquid metals. We're not the only ones. We're just one of many. And I don't want to spend too much time talking about other groups, but there's lots of groups actually in China. I just showed one here, Professor Liu's group. All over the world. Some of these are United States groups, European groups, Australian, Korean. I think I've tried to mention a bunch of different places, but it's really all over the world, and there's really beautiful work being done. It's actually difficult to keep up with this field because it's growing so fast. There are some really exciting opportunities. One is, like I've sort of highlighted in my talk, and that is making soft devices. So this was an artificial eye that was published in the last year in Nature. This is not by my group. I'm highlighting other people's work. Really exciting work out of Australia from the authors listed here who happen to be friends. They showed a way of basically eradicating bacterial films by using liquid metal particles that respond to magnets. This is a big deal because bacterial infections are starting to grow resistance to antibodies. So, think about what's happened with COVID. Now, imagine you start getting bacteria that can't be treated with, antibacterials. It could be a very big problem in the future. And liquid metal seems to have some really nice antibacterial properties. This is some additional really beautiful work coming out of Karash's group down in Australia. And what they showed, along with Torben and co-authors, was the ability to use liquid metals to do catalysis, in this case to reduce carbon dioxide, which of course is another huge world problem, and liquid metal seems to be very promising in this regard. And then finally, this is some work from our group, from a really great postdoc in my group named Jinwoo, where we showed that you could take liquid metals and you can actually initiate reactions. So here we take the liquid metal and we put it in some monomer with no initiator, and we just sonicate it. That's all we do. And this is not sonochemistry. This is literally the liquid metal is inducing the reaction. There's other work that confirms this, and you can actually form a gel simply from the liquid metal's reactivity. Okay, I've tried to stay on time, and I think I've succeeded. So I'd like to summarize by saying that I hope that you find liquid metals as exciting as I do. There's many really unique properties of gallium, one of which is this native oxide that's basically a solid shell that forms on this liquid. And this has led us and other people to make things like stretchable wires, soft sensors, 3D printing, and really just, a lot of things that I've shown today. At the end of my talk, I showed this ability to electrochemically control the interface. And I really do think this is the best surfactant ever reported. It can go from a liquid metal, which has the largest surface tension known to man, basically down to zero. So it's really, really interesting. And we've been studying it for a long time, and it's really scientifically complex. And I hope that other people get interested to, help us understand it. This work was done with some really wonderful collaborators who I list here on the right. I hope that I haven't left anybody off, but I'd also like to mention that we have a really great group of students at NC State. You can see there's several Chinese students just in this picture alone. And I really hope that you'll consider to come visit us. Raleigh is a beautiful place. And I hope that I can come visit you in China or wherever you may be listening from. I'd like to thank the folks that over the years have made this work possible, that have provided us financial support. And I will just conclude by leaving this sort of shout out slide to some recent reviews that have come out from our group, as well as some videos that are on YouTube. And we also have a Twitter channel, which I occasionally update. I'm not very active, but I'd be happy if you would follow us. So I think I ended right on time. Thank you so much. I'd be very happy to answer any questions that you have. And please email me if I don't get to your question tonight.
Okay, thank you, Michael. Thank you for really wonderful and inspiring talk. So, because Professor Zhang is still collecting the question from the audience, so okay. Now I will take the opportunity to ask you 2 questions. So
okay, thank you.
First, so I just wondering for your liquid metal drop test, is that the experiment performed in a vacuum state?
Mm-hmm.
So you drop the liquid metal inside a rough surface and a smooth surface. So to compare the state.
The dropping the droplets.
So that's
Yeah.
This one is is it in a vacuum state? Is can
Yeah, so these experiments, I'm sorry, I'm getting to the slide. These
yeah.
experiments are done in air.
Oh, in the air. Okay. So this
Yep, and they're
means
high. Go
so
ahead, please.
so the surface will keep will get oxidized, right? By the air,
Exactly.
right? So this
Yep.
kind of droplets. So
Yeah,
you
so
first.
if you did this experiment in vacuum, the droplets would just bounce off the surface because
Okay.
they don't. Yeah. So the really the amazing one is this one on the right, which is I don't know if you can see, but the droplet actually completely sticks to the surface.
Okay.
So so liquid metal, remember, liquid metals have the largest surface tension. It's like almost 10 times bigger than water,
Okay.
which means it should form a sphere. And this instead of bouncing off the surface, it's like sticking, like putty. And it's entirely because of the oxide. Now, if you make the surface rough, the oxide doesn't stick and it can actually bounce back.
Okay. So from the if in terms of wettability from the cases now we know that uh, if the surface it is hydrophilic, so when increase roughness of the surface though will make it super hydrophilic. So looks
That's
here,
right.
but look like you said the rough surface will prevent adhesion. So why is this?
So yeah, I'm glad you mentioned the Cassie-Baxter state. So that's it's very similar to what's happening here. Basically, if I go back a couple slides. So this is oops. Give me one second, please. This is there we go.
Take your
This is
time.
the what this is what the surface looks like. So it's
Yeah.
got it's rough, very much like a Cassie-Baxter state. And so what
Yes.
happens, I think, is that the oxide layer cannot make good contact to the surface. So it's like sitting on a bunch of little posts. And so it doesn't have very many contact points. And so it's easier to sort of, peel the oxide off of the surface. One thing that's interesting that's different is that this surface, the chemical composition doesn't matter. So
Okay.
we can make this fluorinated, like super hydrophobic, and it works. But we can also make it hydrophilic. We can make it like with hydroxyl groups, and and water will wet it, like perfectly wet it. But the liquid metal
Okay.
doesn't stick. So it's really the roughness and not the chemical composition of the surface that seems to matter the most.
Okay. I see. I see.
Yeah,
Thank
that's a
you
great
very much.
question. Yeah, it's really interesting.
Yeah, I think I actually this is really eye-opening talk to me. So I really inspiring. I think liquid metal definitely is very magical materials. Yeah. So
I've heard people I think so too. I've heard other people call it that, but it really is. It's got so many unique properties. It's really special.
yeah, sure. Yeah.
And I
So
only talked
Professor
about a
Zhang,
few of them.
yeah, yeah. I think your talk is very inspiring and with a lot of cool applications. Yeah, I really learned a lot from the talk. Yeah. So, Professor John, is there any question? So there's a question from the audience side. It is possible to know what is the speed video rate was for the liquid printing of the bubbles.
Oh, that's real time.
Yeah.
Let me go back. So we're talking about the same thing. I think we're talking about this one, and this is
Yes,
real
yeah.
time. Yeah, this is real time. So the oxide layer forms in like microseconds. So it's I'm sure we could print even faster if we needed to. When we made this video, this was actually done by a really good undergrad in my lab, and he
Okay,
did this
wow.
manually. Like he had
Yeah.
to like manually do this. Um, so it's a little confusing, but technically this video is sped up, but we can print much faster than this.
Okay.
I can't remember how fast we can print, but oh shoot. But if you see right here, um, okay, right after this, I'm gonna pause it right here, okay. What we're going to do is a burst of pressure. And when we do the burst of pressure, it will shoot the metal out as a cylinder and form an oxide layer. So it forms really fast. Boom.
Okay, wow.
So in principle, we could probably, you could print very, very fast. We just, actually, I don't think we've really tried to push the limits. It's probably limited by our machine and not the
Yeah, I think
material.
so.
Yep.
Okay, so there is another question from the audience. So for the wetting part, so what's the difference of your technology compared with the traditional electrowetting?
Oh, that's a great question.
Yeah.
There's a huge difference. So let me find that slide. This is a very, very important question. Thank you. So in traditional electrowetting, what you do is you apply a voltage between your liquid and your substrate.
Yeah.
And typically you put an insulator on your substrate to avoid chemical reactions from occurring. So
Yeah.
that's what's called electrowetting on dielectric. Now, when you do that, when you apply the voltage, droplets can start to change their contact angle
Yes.
and sort of wet more, right? Now, when you do that, what you're fighting against is surface tension. Surface tension wants it to be a perfect drop, and you apply the voltage, and it will spread out. In the case of liquid metals, they have the largest surface tension of any liquid. So if you want to get a small change in contact angle, you need to literally apply 100, 200, 300 volts, something like that, like hundreds of volts. Here, we're applying 1 volt, okay, 1 volt. And the counter electrode is not the substrate. The counter electrode is up here. You can't see it. And so this is not an effect of electric field. It's not an effect of electric field forces. It's simply because we're depositing species on the surface electrochemically. So when we do this, again, 1 volt, not 300 volts. It's much, much smaller. And secondly, if you watch, when it starts spreading, the contact angle actually never changes or doesn't change very much. And so with electrowetting, you actually change the effective contact angle. Here, all we're doing is lowering the tension, and gravity is just causing it to sag down. So it might be easier to see with this cartoon. Again, there's an electrode here. The counter electrode is like here. You can't see it. And if you look at the contact angle, we're not actually changing it. It's just sagging down.
Okay.
So this is completely different phenomenon. It's not electrowetting. And
So
that's
this is
why it's
just
so
because of
exciting.
the gravity of the liquid metal, right? To
Yes.
make it spread out on the surface, right? I see.
Yes, and yes, that's correct. And then, but then when we see this, there's also we think what's called Marangoni effects, which is gradients in surface tension. But I mean, I'm sorry, I'm getting excited because I just think this is so interesting. But if you think about it, if you think about like water, right? Water
Yeah,
doesn't form these shapes. If you think about
sure.
a snowflake, like a crystal, if you hold that in your hand and it melts, the first thing it does is forms a droplet of water. It forms a sphere.
Yeah.
And we're taking a liquid with 10 times bigger surface tension approximately, and at 1 volt, we're getting fractals. We're not doing anything. We're just applying 1 volt. That's it. And we get these like crazy shapes.
Yeah. It's very
So
interesting.
again, it's not electrowetting, it's electrochemistry.
Okay.
Yep. I'm
So
so glad somebody
basically,
asked that.
yeah. So basically, to show this kind of liquid metal spreading, so probably the size of the droplet should be very important, right? If the droplet is too small or the droplet is very huge, probably this kind of change is not very obvious, right?
Yes. Yeah, that is right. Yeah. So um you have to keep in mind the different forces that are involved, right? So as long as the droplet is big enough, then you can get gravitational effects. You're okay. And in fact, when we did this flowing experiment, these are actually pretty small. So the diameter of this nozzle is 100 microns. So it's actually quite small. And when you pump it out, you see. So let me pause it if I can. Let's see. Right. I don't know if I can do it. Like right there. So this droplet is staying on the nozzle because of surface tension, and it will get bigger until gravity causes it to fall. So we know there's a balance between surface tension and gravity, and we've quantified that. I don't have the data here. And what's interesting is that as that tension gets lower and lower, if you watch the voltage, it's going a little higher and higher. At some point, the surface tension basically goes to zero, and it comes out as a perfect cylinder. And so I'm kind of answering your question in a roundabout way, but yes, the size does matter because it affects the gravitational forces. And I don't know how small of a structure you can do this on, but you can see here we've done it down to 100 microns or so, and it works.
So, okay. So there's a question from the audience. He said, what will happen if the diameter of the needle is changed?
Great question. So in this project, I assume you're talking about this project. In this project, we saw that to a first approximation, the diameter of the liquid metal, which actually you can really see better here. Let me pause this. In this video, the diameter of the wire, which is you can see falling, is basically almost exactly that of the syringe. So, for example, if this is 100 microns, then the wire that comes out will be about 100 microns. And if you're talking about the 3D printing, we also found the same thing. So when we were doing the printing, we found that the printed structures were about the same size as the needle. So, there's kind of a limit on, at least for us in our lab. This is about the smallest nozzle we could make. We had to do it in kind of a special way. But, it's possible to go smaller. I think inkjet printers use 50 micron nozzles, so it should be possible to go smaller.
Okay. So I have additional question that is
Okay, great.
So you said you apply 1 volt voltage, then you can change the shape of the droplet when contact with other surfaces. So this 1 volt is a constant value or is a droplet size dependent?
Oh, well, that's a good question. So it's a it's a really good question, and I'm trying to think if I have the right slide here to answer it. So let me go back. Okay, so I'm gonna show you this. So in this slide, there's a plot of surface tension versus potential. And the surface tension when we're in sodium hydroxide is like 500. So it's really, really large. Remember, water is like 70. So water is like down here. So the droplet looks almost perfectly spherical. Now, when we start applying the voltage, which again, remember we do from the bottom, you'll see it looks like we're applying negative 1.5, but this is actually 0. This is just what's called the open circuit voltage. So we're not applying any potential. It's just what happens when you stick the electrodes into the electrolyte. So when we start the experiment, you'll see that the droplet starts to squish some more. So you see the tension gets lower and lower, and then it goes back and completely reversible. So we're going from very large tension, like 500, and you can see it gets lower and lower and lower and lower. And then at some point, it actually looks like it's going to go to 0. And that's exactly where we see the fractals. That's also exactly where we see that wire. So if you form fractals, that means the area, there's no penalty for forming more area. And that's essentially what we're seeing, is that as the tension gets lower and lower, right around this voltage. So negative 1.5 to negative 0.5, that delta is about 1 volt. So that's why I said 1 volt. That's where we get this really low surface tension. Now, your question was about, what is the effect of this droplet diameter? And what we see is that for most of this potential range, for the sizes that we've measured, which I don't remember off the top of my head, but for the different droplet diameters, we see the same behavior. We see the same physical behavior. Now, if you start going to higher voltages, which I don't show here, but somewhere like out here, you do start to see a dependency on the droplet size. And I believe that has something to do with transport limitations. Basically, how fast species from this solution can get to this interface. So you might remember in this video right here, remember we started applying the voltage. So we're applying 0.2, 0.3, 0.4. You see the droplets get smaller, 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 smaller. And then 0.8, this is kind of the magic number. That's where we get the wire. But if you go to higher voltages, you start seeing this like really weird, like thicker oxide. That transition does depend on the droplet size or the droplet flow rate.
Excuse me? So Professor Zhang. Okay, Michael, you continue, yeah.
No problem. That's really it. I mean, I was just going to say that it's probably if the short answer to your question is it doesn't matter the droplet size, but it does matter at higher voltages. That's the short answer to your question.
So you mean there's a threshold voltage for this kind of observation, right?
Yeah. So basically, this is driven by electrochemistry, and so as you know, you need to achieve certain electrochemical reactions. You need to apply a certain potential, and so because of that, that's why the droplet size doesn't really matter up to a certain point. And so, yeah, so to get this, like the really interesting behavior, it's about 0.8 volts relative to the open circuit voltage. Yep.
Okay.
But again, but the tension keeps dropping. So if you look at the droplet as this happened, it gets like flatter, 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 and then suddenly it starts forming the fractals.
Yes.
So.
Okay. Yeah. Thank you, Michael. Thank you very much for your wonderful talk. I think.
Oh, you're welcome.
Yeah. So for the audience, if you have further questions, you can send an email to Michael, and then I think he will reply your email. Yeah. So
I would love to hear from you. So please do.
Hi, Professor Michael. Also, thanks for your wonderful talk, and thanks for Professor Junsen's excellent host. Okay, and welcome to submit your work to SmartMath. Yeah, thank you.
Oh, thank you. Thank you, everyone, for being here.
Take care, Michael. Take care, Professor Zhang. Thank you.
Thank you so much.